We introduce a theory describing Fermat paths in the context of non-line-of-sight imaging, and show how it can be used to reconstruct the shape of objects outside the line of sight of a sensor. By non-line-of-sight imaging, we mainly refer to two scenarios. In the first scenario, we have an active light source and a sensor, which are collocated and are looking at some diffuse surface, for example a wall. The scene also contains an object that is outside the field of view and completely occluded from the sensor. We then want to use measurements captured by the sensor to reconstruct the shape of this object. We refer to this scenario as looking around the corner. Alternatively, the object may be within the field of view of the sensor, but occluded from it through some optically thick diffuser, for example a piece of paper. We refer to this scenario as looking through a diffuser. In both of these cases, the light source illuminates a point on the visible surface, wall or diffuser, and this point scatters light in all directions towards the non-of-sight scene, acting as a virtual source. Similarly, the sensor images a single point on the visible surface. This point receives light from all directions from the non-of-sight scene, acting as a virtual sensor. In both cases, we assume that our source and sensor create a transient imaging system. This means that in the end, we measure not just a single intensity, but a histogram of intensities for different times of light in the non-of-sight scene. We call this histogram a transient. We see that both of these cases, looking around the corner and looking through a diffuser, can be equivalently described as an imaging scenario where an object receives light from a virtual source and sends light towards a virtual detector on some surface. For this presentation, we will assume that these two virtual points are collocated. In the rest of the presentation, we'll be using a 2D visualization of this non-line-of-sight imaging scenario. Additionally, for convenience, we will flip our scene upside down. And finally, we will not be the actual source and detector, acting as if the photons directly start and end in the virtual source and detector. Let's now look at the transients we measure in this non-line-of-sight imaging scenario. Our first observation is that these transients will be discontinuous at a number of locations. In the example shown here, this happens at two locations which we mark with blue and red. We can prove that these discontinuities happen at times that correspond to the length of paths in the scene that satisfy Fermat's principle. That is, paths that are locally shortest or locally longest. We can additionally prove that these Fermat paths will be of one of two kinds. The first kind are specular paths, meaning that they connect the virtual source to a point on the non-of-sight surface, such that this connection is parallel to the surface normal at that point. The second kind are paths corresponding to points on the boundary of the non-of-sight surface. For an object of general reflectance, there will be some photons that travel along these Fermat paths, producing the discontinuity of the transient. There will also be photons that travel along paths that are not Fermat, producing the continuous parts of the transient, and an example is shown here in gray. Even though we cannot measure these two types of photons, Fermat and non-Fermat, separately, given a transient, we can still identify the lengths of all the Fermat paths that contribute to it by finding the times where the transient is discontinuous. We can prove that these Fermat paths and their lengths have a number of useful properties. First, Fermat paths are a function of only the geometry of the non-of-sight scene and not its reflectance. What this means is that the locations where a transient is discontinuous will remain the same regardless of the BRDF of the non-of-sight object. Second, by knowing the length of a Fermat path, we know that the corresponding point on the non-of-sight surface will be on a sphere, with center the virtual source and radius equal to half the length of the Fermat path. If the Fermat path is a specular path, then this sphere will additionally be tangent to the non-of-sight surface. Third, Fermat paths satisfy a property that we call the Fermat flow constraint. This property says that the spatial gradient of their length with respect to the virtual source is parallel to the direction connecting the virtual source and the point on the non-of-sight surface. We can think of this spatial gradient as follows. We slightly perturb the virtual source by some distance and measure by how much the length of the Fermat path changes. The ratio of these two, as the perturbation becomes smaller and smaller, is the spatial gradient of the Fermat path length. The Fermat flow constraint says that if we know the length of a Fermat path and its gradient, then we can reconstruct a point on the non-of-sight surface through a simple geometric operation. We intersect the sphere we described earlier, center the virtual source, with a line that is parallel to the gradient and passes through the virtual source. The point of intersection will be the point on the non-line-of-sight surface. Additionally, if the Fermat path is specular, the gradient also gives us the surface normal at the non-line-of-sight point. Unfortunately, even though we can indirectly measure lengths of Fermat paths by finding the locations of discontinuities in non-line-of-sight transients, we cannot measure their gradients. However, we can estimate these gradients through interpolation by considering transients measured at nearby virtual sources. Our pipeline for non-line-of-sight reconstruction is based on this observation, and it works as follows. First, we scan the virtual source on many different locations of the line-of-sight wall. Second, at each one of these locations we measure a transient. Third, for each of the measured transients, we detect the locations where they are discontinuous, and these locations correspond to lengths of Fermat paths. For each detected Fermat path length, we can estimate its gradient by interpolating between the lengths of Fermat paths from measurements in nearby virtual sources. Finally, given these pairs of Fermat path lengths and their gradients, we can reconstruct the point cloud and surface normals corresponding to the non-line-of-sight object. This oriented point cloud can be used as input to an algorithm such as Poisson surface reconstruction to finally produce a continuous surface corresponding to the non-line-of-sight object. This reconstruction pipeline can be used anytime we have transient measurements, regardless of the kind of transient imaging technology. To demonstrate this, we saw non-line-of-sight reconstructions we obtained using measurements from two very different transient imaging systems. The first system uses a single photon avalanche diode and a pulsed laser to capture transient picosecond resolutions. We use this system to take measurements of a variety of tabletop objects in the looking around the corner setting. Here are a few examples of objects we measured and their reconstructions. We see that our algorithm can reconstruct Lambertian, semi-transparent, glossy, and specular objects of complex geometry, both convex and concave, at an accuracy of a few millimeters. The second system uses optical coherence tomography to capture transients at a resolution of a few femtoseconds. We use this system to take measurements of a US quarter coin in the looking around the corner setting. We use the same system to additionally take measurements of the coin in the looking through a diffuser setting. Here are our reconstructions compared against a scan obtained with the same coin directly in the line of sight of our optical coherence tomography system. We observe that in both cases, our algorithm can reconstruct very fine detail on the coin, enough to distinguish its denomination. For additional results and for more details about the theory of Fermat paths, we refer to the main paper. Thank you.